we have been looking at the Parsifal's theorem, and either as a consequence or as an issue in itself, as a derivation in itself, we've been looking at the multiplication theorem, right, which tells us that if you multiply two signals, their Fourier transforms are convolved. We've also seen how there is no clear cause and consequence relation. Any of them could be thought of as a cause and the other as a consequence, right, which really goes to say that there are only certain small set of fundamental truths in the Fourier transform, and most other results or most other known derivations or theorems come from those truths in one way or the other. And sometimes the sequence is not important. One might arrive at one conclusion first and the other conclusion later, and there is no real clear sequencing of ideas there, right? This should be understood very clearly because it is important to understand the linkages between different consequences or between different results in the context of the Fourier transform. Today we look at one further such important result in the context of the Fourier transform. We had shown yesterday that the Fourier transform of a cross correlation is the product of the Fourier transforms with the second complex conjugated. Yeah? So we showed that if we consider integral x t plus tau y t bar dt, by using the Parseval's theorem, one might write this down in the frequency domain, and one can show that it's nothing but integral xf y bar f e raised to the power j 2 pi f tau df, which happens to be the inverse Fourier transform of xf y bar f evaluated at tau. Think of tau now as a time variable. This is a function of tau. In fact, we gave this a name. We call this rxy tau. Yeah? We also mention an importance of rxy tau in the context of signal processing, in the context of dealing with signals and systems. The importance was as follows. You see, suppose, let's take a physical situation. Let yt be the received waveform when xt was transmitted from a location very distant. So we have a transmitter at a very distant location sending out the waveform xt. Yeah? We don't know at what time this xt was sent. Xt may be a time limited waveform, or it may be a waveform whose significant amplitude is only in a certain region of time. Even if it is not strictly time limited, that means it may have insignificant or very small amplitudes after a certain interval of time. It's only in a certain interval of time that the amplitudes are significant. Right? In what physical situations can this happen? Suppose there's a radar which is transmitting pulses. I'm sure all of you have heard the term radar, radio detection and ranging, essentially to use electromagnetic waves for being able to detect and come to a conclusion about location of targets. That's what radar does. So suppose we have a radar which sends out pulses and tries to locate a target. Right? The radar receives a waveform reflected from the target after a certain interval of time. And if in a very simplistic situation, if the target is stationary, even if the target is stationary, because of the interleaving channel, by channel we mean the medium that separates the radar from the target, it could be just the atmosphere, or it could be some other solid medium or liquid medium, yeah. There is a distortion of the waveform, or there is an addition of noise to the waveform. But we hope the distortion is not so serious that the received waveform is entirely different from the transmitted waveform. It's close but not quite the same. Right? In that case, this kind of an idea is very important. At the radar, what we effectively do is to take the cross correlation of the incoming waveform with the waveform that has been transmitted. And we look at the magnitude of the cross correlation. The magnitude of the cross correlation would show a maximum at a value of tau, which denotes the time at which the waveform was reflected from the target. Or just, the idea is like this. Suppose you have a waveform xt transmitted from the radar. It takes 1 second to reach the target and 1 second to come back. Then we, in an ideal situation, in a situation where the interleaving medium is perfect and there is no noise, we expect that the received waveform will just be a replica of the transmitted waveform but delayed by 2 seconds. So if we take a cross correlation of the received waveform yt with the transmitted waveform xt and evaluate it for different taus, we shall see a maximum at tau equal to 2 seconds, which indicates the target is at tau by 2 second away, half that time away. Right? But the interesting thing about the cross correlation is even if the received waveform is not exactly equal to the transmitted waveform but approximately so, it will still show a maximum at tau equal to 2. And therefore, it shall indicate the position of the target even in the presence of noise. So the concept of a cross correlation is extremely important in the context of detection. Detection problem is facilitated by cross correlation. Yeah? And because of this relationship, this tells us that the cross correlation can also be thought of as the inverse Fourier transform of the product of the Fourier transform xf and y bar f. This gives us an interesting way to calculate the cross correlation, which might sometimes be very convenient. We could take the Fourier transform of the waveform that we've transmitted and multiply it pointwise with the Fourier transform of the incoming waveform. That might be so much more efficient to do at times. And then calculating the inverse Fourier transform of this product would lead us to a position of maximum, which can, therefore, it is sometimes easier to carry out the detection problem entirely in the domain of frequency. Yeah? Yes, Uday.
Why do we need to take the inverse?
Why do we need to take the inverse? Because you need to find out the position tau at which you have a maximum. That's a time expression. Yeah? The question is, why do you need to take an inverse Fourier transform? Yeah.
Right hand side, so I don't need to take the inverse of the right hand side.
No, I need to take the inverse of xf y bar f. I need to take the inverse of xf y bar f. Right? That gives me rx y tau. Now, in particular, if yt is equal to xt, what do we have? We have a quantity called rx x tau. And this is called the autocorrelation of x with itself. We don't have to say with itself, because autocorrelation means with itself. Right? So, it's called the autocorrelation of x. And in that case, what is the Fourier transform correlation by this principle? Rx x tau has the Fourier transform f x bar f, which is mod xf squared. This is a very interesting result by itself. Right? What is this saying? This is saying that the magnitude squared of the Fourier transform has a physical significance. Its inverse transform is the autocorrelation function. This principle is very important. Right now we are dealing with deterministic signals. Deterministic signals means signals for which at every point in time there is a well-defined value. And all through this course we will really be dealing with deterministic signals. I mean, at least if at all we talk about signals that are not deterministic, it would only probably be towards the end, and that too for a short time. So we are talking about the first course on signals, we talk about deterministic signals. And this result has been proved in the context of deterministic signals right now. But the same result carries over to what are called non-deterministic or stochastic signals. I thought I should mention this. This is important because the corruption that a channel poses, that the medium poses on a waveform that is to be detected is non-deterministic. So unfortunately, even if the radar transmits a deterministic waveform, what is received is often a non-deterministic waveform. And this idea still carries over to the domain of non-deterministic waveforms as well. Right? I thought I should just mention this because it gives us the context. Now coming back to this, what does it tell us? It tells us that the autocorrelation has for its Fourier transform the magnitude squared of the Fourier transform of the function itself. Right? Now let's look at a particular example of a point f. So you see, what we'll do is we'll look at we'll look at a small region around the point f equal to f0. So this is let's assume that this is xf. Of course, if we assume that the signal is real, its magnitude is symmetric. So its magnitude squared is symmetric, and therefore this could be an example of a magnitude squared. Now let's look at another function ht whose Fourier transform is just a narrow pulse around f equal to f0. And of course symmetrically on the other side, minus f0. So we'll assume that this is the Fourier transform hf, and therefore mod hf squared is also this. Now if we convolve xt with ht, the Fourier transform of the convolution would be xf times hf, which is let's assume it is yf. So yf is xf times hf, or yt is x convolve with h, evaluate at t. Yeah? What are we saying? We are saying that you pass xt, the incoming waveform, through a band pass filter. That's a band pass filter, just an ideal band pass filter. What's an ideal band pass filter? A filter, a linear shift invariant system, whose magnitude, the frequency response of which, or the Fourier transform of whose impulse response is one only in a certain band around a center frequency. Let's call it f0. Yeah? So when you pass xt through a band pass filter, the result will be to preserve only this part. Now as we narrow this band to be smaller and smaller, but keep the area of this the same, yeah, and equal to 1. So we could visualize a situation where you keep narrowing the band, but keep the area at 1. So of course then you should think of this as moving towards an impulse. So now we brought in the possibility of impulses in the frequency domain. Well, that apart, what is the physical significance of mod? Let's look at the physical significance of both this integral, all right, as also the integral mod xf squared over all f, right? So first let's look at the physical significance of the integral of mod xf squared over all f, right? So we use Parsifal's theorem. Parsifal's theorem says integral xt x bar t dt is equal to integral mod xf squared df, or xf x bar f squared df. So what are we saying here? What are we saying in effect here? We are saying that, see, what is this quantity really? Mod xt squared. Well, for a function that has finite energy, mod xt squared dt is the energy in the function. And what this tells us is that the energy of the function is the same whether calculated in time or frequency. So we can also calculate the energy in the function by integrating mod xf squared. So that's the physical significance of the area under mod xf squared. It's the total energy in the function xt as a consequence of Parsifal's theorem. But as a particular consequence of this, what is the physical significance of the area under this? It's the energy in the function around the frequency f0. So it's like a density of the energy. Just as, for example, if you have a mass, and if you look at the mass per unit volume, its density, right? So here you're looking in some sense at the energy per unit frequency, that's the density. And if you integrate the energy per unit frequency over a region of frequency, it gives you the energy. So if you integrate the energy density over the frequency, here density is with respect to frequency, then you get the energy. So therefore, the physical significance of mod xf squared is an energy spectral density. It tells us the way in which the energy is distributed over frequencies. Yeah? So we give it a name. We call mod xf squared the energy spectral density. Of xt. Now I must caution the audience about the difference between density and point mass. When you have a density of energy mod xf squared which has no impulses, just as when you have a mass without any point masses, then the amount of mass in a zero volume is zero. So the energy at a particular frequency is zero because there is no area under that energy. So although the energy spectral density may be non-zero at a point, the energy at a point can be zero, whether in time or in frequency. So here again we now need to bring in the idea of being able to concentrate energy into a point on the frequency axis. And in fact that idea shall be related to moving from aperiodic or finite energy signals to periodic or infinite energy signals. The moment a signal is periodic, its energy is infinite, because in every period it could have finite energy, and therefore the total energy tends to infinity. So we cannot really deal with periodic signals in the framework that we have directly. We need to modify it by introducing the idea of concentrating the spectrum into a point, and that we have done before in time. We have done it by bringing in impulses. So now we shall slowly move towards bringing in impulses in frequency as well. So let us bring in an impulse into the frequency domain. Let us bring in just one impulse. This is the frequency axis. We put on the frequency axis just one impulse at the location f equal to f0. Let the height of this impulse be k0. This is an impulse. We find the inverse Fourier transform of this, right? So how do we express this function? We express it as k0 delta f minus f0. What is the inverse Fourier transform of this? What is the corresponding xt? If this is xf, what is the corresponding xt? xt is is integral xf e raised to the power j2 pi ftdf, which then becomes integral k0 delta f minus f0 e raised to the power j2 pi ftdf, which clearly is equal to, well, what does this impulse do? It simply picks up the value of this at f equal to f0 and puts that out. So it gives you k0 e raised to the power j2 pi f0t. So that's a convenient interpretation. It tells us that an impulse in the frequency domain located at f equal to f0 corresponds to a complex exponential. What does it also mean? It also makes a negative statement. The negative statement is that if you have a function xt whose spectrum has no impulses, and if you ask is there a particular e raised to the power j2 pi f0t present, the answer is no. No particular e raised to the power j2 pi f0t is present. But if you ask how much of energy is contained in a region of the spectrum around a particular point f equal to f0, that can be determined by integrating mod xf squared in the region around f equal to f0. So it must be very clear that as to the difference between the presence of a particular complex exponential in xt and the presence of a range of complex exponentials in xt. In signals that are aperiodic and have finite energy, what is present is a range of complex exponentials with a certain density. Now you see, we often don't pay enough attention to the remarkable result that the Fourier transform gives us when we look at some particular functions. For example, suppose we look at the function, the rectangular pulse, right? So we look at the rectangular pulse. Yeah, in time. Its Fourier transform is of the form sin f by f. It's not important. I'll just draw the sketch. This is what the Fourier transform looks like in magnitude, right? It's a sinc F pattern, sinc BF pattern, let's say. B is a constant. Now, what is the statement that we are making here? The statement that we are making here is that, you have an infinity. I mean, if you, for example, if you look at, let's assume you look at this range of the f-axis here. That gives you a certain set of complex exponentials. Those complex exponentials are actually present over all time. E raised to the power j2 pi ft for this region of f, each of them is present for all time. But the interesting thing is that because of this clever combination of amplitudes and phases, it so happens that all of them add constructively in this region of time and destructively in all the remaining region of time. So it's remarkable. You have so many functions, all of which are really present over all time. But by suitably and cleverly controlling their amplitudes and phases, you've been able to tune them in such a way that they totally cancel out for, for outside the region of the rectangular pulse and totally, go together and become a constant in the region t between mod t between minus t, t between minus t and t. If you think about it, it's a remarkable statement that we are making. This statement has much deeper implications. I thought I'll just make some qualitative statements. You see, we are all familiar with the idea of, thinking of matter and energy as one thing. Right? I mean, we not exactly know all the mathematics behind it, but we know from, our courses in physics, so we've been exposed to the idea that there is a close relationship between matter and energy. And in particular, if we think of energy as electromagnetic energy, what we are saying is that, if you think of a large number of electromagnetic waves of so many different frequencies, appropriately controlled in amplitude and phase, they could add up so that they all concentrate in a certain region of space. That's what matter is, in a certain sense. I'm just making a qualitative statement. And in fact, what we are doing here is indirectly a statement of that, if you think about it. Yeah, it's possible, even if you have electromagnetic waves actually which are sinusoidal over all space, right? See, what we are saying is that each of these points really corresponds to functions that are present in all time. So similarly, you could have electromagnetic waves that are present all over space. But if they all, conspire, so to speak, and, adjust their amplitudes and phases in a clever way, it's possible to make the resultant concentrate into a certain region of space. So it's a very powerful idea. If you think about it, it's a very powerful idea. Anyway, what it also means is that if you look at the energy at a particular, so it really means that there's no particular electromagnetic wave, there's no particular frequency present. So if you ask how much is the energy at a particular frequency, it's zero. But how much is the energy in a range of frequencies, it can be found out. Right? Now coming back to the idea of impulses. So you see, what is an impulse? An impulse is a concentration of the transform into a point. And what do we mean by concentrating the transform into a point? It means producing just one wave, just one sine wave. So it's very interesting. This also brings out another very interesting property of the Fourier transform. When you concentrate in one domain, that means when you concentrate, for example, in frequency, you spread out completely in time. Can you see that? When you concentrate, in fact, even in this case, you can work it out as a function of t, the rectangular pulse. You see, if you look at the spectrum of the rectangular pulse as a function of t, the larger the t, the narrower the spectrum. In fact, tell me, what will happen as t tends to infinity? It will become an impulse located where? At zero frequency. What does it mean to have an impulse at zero frequency? It's a DC, right? It's a flat function, it's a constant function for all time. So as you narrow the pulse, the spectrum broadens, and conversely as you broaden the pulse, the spectrum narrows. And this is always the case in the Fourier transform. In fact, this is a special consequence of the scaling property of the Fourier transform. Now, I also bring at this point another very interesting issue in the context of the Fourier transform, which also has a very important physical significance. See, here we are talking about narrowing in one domain and broadening in the other. How much can we narrow in both domains? So, the first question is, can I narrow completely in both the domains? That means, can I have a function which is non-zero only over a certain region of time and non-zero only over a certain region of frequency? Well, the answer is not easy, but the answer is no. It's a very, very important result, or a very basic result of the Fourier transform. I shall not prove it. In fact, I challenge you to try and go towards the proof if possible. Right? So, it is not possible to have a function which is completely concentrated in a certain region of time. Forget about a point in time. I am not even asking for a point in time. I am talking about a region of time. So, give me a region between t1 and t2 in time. Give me a function concentrated only in that region. That means it's non-zero only over that. I am not even asking for impulses. Right? So, function is non-zero only in an interval between t1 and t2. And the Fourier domain, it's also non-zero. The spectrum mod xf squared is non-zero only between two frequencies f1 and f2, possibly positive or negative. I don't mind. Unfortunately, this is not possible. So, I put it as a challenge before you to try and see if you can go towards the proof, or even perhaps prove it. Not easy, but certainly very interesting. All right, if not such a stringent thing, can we do something weaker? So, we've already seen that mod xt squared is like, now just as you can have an energy spectral density, you can have a time spectral density. So, mod xt squared is like the density of the energy spread over time. So, you can have a time spectral density and you can have a frequency spectral density. And I shouldn't say, actually I shouldn't say time spectral density. I should say energy time density and energy spectral density. Spectrum is frequency, right? So, energy time density, energy frequency density. So, energy time density mod xt squared. Energy frequency density mod xf squared. So, maybe I should not ask for xt to be non-zero only in a small interval of time. What I shall say is, I won't fix, I'll say take 98% of the energy, right. So, tell me a region in which 98% of the energy lies, say let that region be T1 to T2, and also tell me a region in which 98% of the energy in frequency lies, let that be F1 and F2. So, between F1 and F2 there is 98% of the energy in the frequency domain, and between T1 and T2 there is 98% of the energy in the time domain. So, I have a spread in time defined by T2 minus T1 and a spread in frequency defined by F2 minus F1. Now, can you make those two spreads arbitrarily small? If I fix a limit, for example, suppose I fix 95%, can you give me 0? That means, can you give me a situation where one of them, or where one of them is, so of course, it can be shown that it is possible to come out with, finite limits for both here. That means, if I am not asking for 100% concentration, right? So, if I am not asking for 100% concentration, it's possible to come out with a limit. In fact, that you can see even in the context of the sync pulse. You can always, you can look at the spectrum, and if you integrate the spectrum over a certain region of frequency, it will give you some fraction of the energy. And that fraction of the energy, you can see the time region in which it will give you that fraction of the energy also. Not too difficult. So it's clear that if you don't ask for 100% concentration, you can get a certain finite region of time and a finite region of frequency in which all the energy is concentrated. It's 98% or 95%. Depending on the number that you ask for, you will get different regions. But now, what is the problem? The problem is, can I make the two arbitrarily small? Well, can I make one arbitrarily small? Certainly. Why not? Of course, I can always squeeze the function as much as I want. I can squeeze it and multiply it by a constant. So it will keep the energy can be concentrated. But what will happen in the spectral domain? It will spread. So in one domain I can concentrate. But what about the other domain? So can we simultaneously? So that means what should I look at? I should look at a product. Suppose I look at the product of the region in time, T2 minus T1. So let me call it delta T. A delta spread in time multiplied by a spread in frequency, where spread in time and spread in frequency are understood not in the sense of 100% energy concentration, but some 98%, 95%, 90% energy concentration. Can I make this product arbitrarily small? That's another fundamental question. What do you think? Predictably, the answer would be no. And again, predictably, the proof is difficult. But it's a very fundamental principle. In fact, you know this principle, but you don't know it in this language. Yeah, say that loudly. Yeah. So here we have an answer. So Samir says he knows what this principle says.
This is the uncertainty principle.
What does that mean? What does the uncertainty principle say?
So you can't simultaneously define to arbitrary accuracy both the frequency and the time.
Okay, very good. How is the uncertainty principle known in physics more commonly?
So delta E delta T greater than or equal to H cross.
Very good. Or
delta P delta X greater than or equal to H cross.
That's right. Very true. Surprising, right? So, where is energy, where is time, where is momentum, where is position, and where is time and frequency? What is the connection? But it turns out that Samir is correct. What we are saying here is an avatar of the uncertainty principle. The uncertainty principle has many forms or avatars. They are all really the same essential thing. The essential thing is that a function in its Fourier transform cannot be localized simultaneously to an infinite extent. But this has many manifestations. One manifestation is the fact that you cannot simultaneously locate position and momentum with infinite, or if you constrain position, then momentum cannot be constrained infinitely. In informal language. See, we must understand it more formally when you actually look at the uncertainty principle carefully. The other consequence is that energy and location in time cannot be constrained infinitely. And the third manifestation is this. And there are so many other manifestations. And this manifestation has a very important bearing, just as the physical or the physics version of the uncertainty principle is sometimes the gap between modern physics and traditional physics. The uncertainty principle in signal processing is also a sense the gap between modern signal processing and traditional signal processing. What are we saying in effect? We are saying that if I am trying to detect a waveform which is localized in time, right? And if I also want, you see, why is frequency important? See, frequency has a meaning in resources. You know that your radio has different stations, your television has different stations. Every operator on the cable is worried about what bandwidth he can use. Bandwidth is a resource, just as time is a resource. Everybody wants to be transmitted on prime time. Time is a resource. Bandwidth is also a resource. Right? So you cannot use any extent of the frequency axis freely. When you transmit, not only must you transmit in a certain region of time, but you will also transmit in a certain region of the frequency axis. If you are talking about AM, it means a few hundreds of megahertz, not more than that. Perhaps not even a few hundred megahertz. So, it's maybe, a few hundred kilohertz. So, the whole point is that just as you have a resource in time, you also have a resource in frequency. And here is where the uncertainty principle hits. Because it tells you, it gives you a negative statement. It tells you that, you can constrain yourself to a usage of a certain region of time, and you can constrain yourself to a usage of a certain region of frequency. But if I look at their product, you can only do so well. You cannot go below this. That's what the uncertainty principle says. And it has direct bearing on communication, on signal processing, on the ability to detect, on the ability to transmit, right? It's a very important idea. So I thought we should discuss these issues qualitatively because they give you a deeper insight into the context of the Fourier transform, and they also explain to you the physical relevance of the Fourier transform and its implications. But now coming back to more formal topics, namely the idea of impulses in frequency, right? I wish to obtain a Fourier series by doing something in the Fourier domain. So I wish to obtain, the first thing that I'd like in the Fourier series is to obtain a function of the form A0 cos omega t plus phi. In fact, this captures the whole story, doesn't it? Because if I can obtain A0 cos omega 0 t plus phi, which is nothing but A0 e raised to the power j omega 0 t e raised to the power j phi 0 plus by 2, of course, plus A0 by 2 e raised to the power minus j phi 0 e raised to the power minus j omega naught t. If I can obtain this term of the Fourier series by drawing a spectrum, I can obtain the whole Fourier series, because in general a Fourier series can be written as a combination of such terms. Right? Now, can we write this term in the Fourier domain? Yes, indeed. What is the spectrum of this function? It's a pair of impulses located at f0 and minus f0. And what are their strengths? The strength of this is the strength here, A0 by 2 e raised to the power j phi 0. And the strength here is A0 by 2 e raised to the power minus j phi 0. Yeah? No. I am working with, since I am working with Hertz frequency, there is no factor of 2 pi. That's why I said it's sometimes convenient to work in terms of Hertz frequency. But we should write the same thing down in omega. In fact, now for that purpose, let us put an impulse at omega equal to omega 1 and see what happens. So suppose I put an impulse on the omega axis instead of the f axis at omega equal to omega 1 of strength k0. What is the inverse Fourier transform of this? It is k0 del omega 1 e raised to the power j omega t d omega, but with a factor of 2 pi. This is the inverse Fourier transform. This is the inverse Fourier transform. Yeah. Now what is this? This is nothing but k0 by 2 pi e raised to the power j omega 1 t. Yeah. So if we wish that the magnitude of this should be 1, then k0 must be 2 pi and not 1. So if I bring the same impulses into the omega domain, so if I just convert this into the omega domain, what must I do? I must put this at omega 0, I must put this at minus omega 0, but I must multiply this by 2 pi. Yes? So now this idea can be extended further. When you have a Fourier series expansion, each term in the Fourier series gives you an impulse on f or an impulse on omega equivalently. And therefore, what is the Fourier transform of a periodic function? It's a train of impulses. It's called a train of impulses. It's a series of impulses located at multiples of 2 pi by t, where t is the period. 2 pi by t is the fundamental frequency. So you have a train of impulses located at 2 pi by t, and the strength of the impulses is proportional to the coefficients of the Fourier series. If you are talking about the frequency axis f, the Hertz frequency, the strengths are equal to the Fourier series coefficients. If you are talking about the angular frequency axis, the strengths are 2 pi times the strength of the Fourier series coefficient. Here strength should be understood as a complex strength, because each Fourier, you are talking about the Fourier term e raised to the power j k times omega naught t, where omega naught is the fundamental frequency, angular frequency. Yeah. Of course, now what you also can clearly see is that for a real periodic signal, the impulse at omega 0 and the impulse at minus omega 0, and so to the impulse at every corresponding positive and negative frequency, would have the same magnitude of strength but opposite phase. That's to be expected. That can also be seen graphically. Yeah? Because when you have two complex numbers rotating with equal and opposite angular velocities, if they start with the same amplitude, if they have the same amplitude and opposite starting phase, they result in a sine wave. Yeah? Right? So that brings us to the idea is that just as we can have impulses in time to concentrate functions into points in time, you can have impulses in frequency to concentrate functions into points in the frequency axis. But a word of caution. Suppose you have a train of impulses. In fact, let's say you have a single impulse. Forget about impulses. Suppose you have an impulse f on the f axis. Let's work with the f axis. You can correspondingly extend the results to the omega axis, right? What does this correspond to? If the strength is, let's say, k, it corresponds to k e raised to the power j omega naught t. What is this? What is the energy in this function? This energy is divergent. The energy doesn't converge. This tends to infinity. This energy tends to infinity. What does it tell you about the impulse? The impulse is not square integrable. So if I try, in fact, that's what it really says, is that if I take mod square of the spectrum and integrate, it would diverge. So an impulse is not square integrable. An impulse is integrable, but not square integrable. That's not difficult to see. What is an impulse? An impulse is a concentration of the following kind. Right? You have a delta and you have a height of 1 by delta. And if you square this would be 1 by delta squared. And 1 by delta squared multiplied by delta is 1 by delta. So if you take the limit as delta tends to 0, it doesn't exist, it diverges. Is that right? So an impulse is not square integrable. But then we do have something like power, don't we? So for example, if you take the function k e raised to the power j omega naught t or k e raised to the power j 2 pi f naught t, we can define the power, that is the energy over a unit period. And how much is the power? The power of this function is 1 by f naught, that is the time period, integral mod k e raised to the power j 2 pi f naught t squared dt. And this is over an interval of t naught, which is 1 by f naught. Yeah? And how much is this? This is k squared, mod k squared. Is that right? It's mod k squared. So you see, I mean, we can conceptualize a power spectral density just as you can have an energy spectral density. So suppose I put on the f axis, an impulse of strength squared here. What is the physical significance of this? This is nothing. If I take the inverse transform of this, it tells me that, it really tells me that there is, there's a concentration of energy of value k squared at the frequency f naught. So this has a significance, right? In fact, this is called the power spectral density of the waveform e raised to the power j 2 pi f naught t. And just as we had a correspondence between the energy spectral density and the autocorrelation of the function, there is a corresponding idea here. When you have periodic functions, then we can define an autocorrelation, but not in the way for aperiodic functions. That's because you cannot integrate over all time, it diverges. So what do? You integrate over a period. So suppose you have two functions, both of which are periodic with a certain period. Now for example, they could inherently be periodic with different periods. For example, one of them may have a period of 2 and the other may have a period of 3. But a function of period 2 is also a function of period 6. A function of period 3 is also a function of period 6. So you can find the least common multiple of their periods. So if you have two functions which are periodic with periods t1 and t2, and if t1 and t2 have a least common multiple, what does it mean? It means that t1 by t2 is rational. When would t1 and t2 have a least common multiple? When their ratio is a ratio of integers. Right? So if they have a least common period, then you can think of both of them as periodic with that period, LCM of t1 and t2. And in that case, you can define a cross correlation between them. Right? So you can define the cross correlation xt plus tau yt bar dt, but here the integral is not over all time but over the common period t, right? It doesn't matter which common period. See, because the functions are periodic, so it could be any continuous interval of t. The integral can be over any continuous interval of t. We write that as in bracket t. This denotes being able to integrate over any continuous interval of t divided by t. This is called where t is the common period y. Now, if xt, if both of them have a common period of t, then in the spectral domain, both of them have impulses located at multiples of 2 pi by t on the omega axis or 1 by t on the f axis. So, you have impulses at points 1 by t, 2 by t, minus 1 by t, minus 2 by t and so on, right. So, just as you did in the context of aperiodic functions, you took xf, yf bar, right. You could do the same thing here. You could take products of corresponding impulse strengths. Of course, the second one complex conjugated. You could take products of corresponding impulse strengths. So, the impulse at 1 by t, you take the impulse strength from x, take the impulse strength from y, complex conjugate, multiply, and write another stream of impulses with this product. Question is, what does that impulse train correspond to? It corresponds to the Fourier transform of this, right. That impulse train, which has impulse strengths given by the product of corresponding impulse strengths with the second complex conjugated, corresponds to the Fourier transform of this. What does it mean? It means the Fourier this cross correlation is also a periodic function of tau and has the same period t, right. So, the cross correlation of such periodic functions x and y, both of which have a period of t, is also periodic with a period t, and its Fourier transform comprises of impulses located at points which are multiples of 1 by t on the f axis, and their strengths are the products of corresponding strengths taken from the Fourier transform of x and the Fourier transform of y. With this, then, we conclude today's lecture and proceed from here in the next one. Yeah, that's the thing. It's not